Hey, we're looking at the AP practice problems. These are cumulative multiple choice problems for AP review. So let's look at number 1 here. Function f satisfies a limit as x approaches 1 of f of x equals 3. So which of the following could be the graph of f? So if a true limit exists, that means the graph is going to have to approach the same y value from both sides. The point doesn't have to exist, but the graph does have to move towards the same y value. Okay, so we're looking for a graph where one side limits both approach 3. So if we look at option A, we see that if we follow this branch towards 1, this branch is taking us towards a y value of 2. This takes us to a y value of 3, so there's not a consistent destination from both sides. So we know that this isn't true. Here, we want the graph to approach a y value of 3. So here the limit does exist, but this approaches from this side is approaching a y value of 2. This side, from this side, is approaching a y value of 2. So the limit does exist, but it's not quite meeting what we want it to be. Option C here, if we're approaching 1 from the left side, follow the arrow, it's moving us towards 3. This is also moving us towards 3. Now, it is true the point is defined somewhere else, but the limit does exist. Now, the graph is not continuous. It won't pass the continuity conditions, but it will pass that second condition of the limit does exist. So the point doesn't have to be at that location for the limit to exist. As long as we have consistency from both sides moving towards the same real number y value, then limit does exist. Here, as we approach 1, this side is approaching y value of 1, this side is approaching y value of 1. It's a continuous function, but it doesn't approach 3. Okay. Number 2. The graph of function f is shown. Okay. Which of the following expressions equals 2? So f of 3. So f of 3, we're asking for the y value. It's not defined here, not defined here, but defined here. F of 3 is equal to 4, so that is not going to equal 2. Limit as x approaches 3 from the left side of 3. As we approach 3 from the left side of 3, we see this is moving us towards a y value of 3. The limit does move us towards 3, even though the point is defined elsewhere. So the limit does approach 3 from the left side. Sorry, approach 2 from the left side of 3. So this one does equal 2. That's our answer. But let's just look at the other options as well. Limit as x approaches 3 from the right side of 3. So that means we're following this branch, moving towards 3, moving towards the x value of 3. It's moving us towards a y value of 6. So that doesn't agree with 2. And then here, limit as x approaches 3, the full limit doesn't exist, because from the left side it's approaching 2, and then from the right side it's approaching a different y value. So no consistency there, therefore limit doesn't exist. Okay, number 3. Function is defined here. Which of the following statement is true? So what I like to do is I like to just, if I see a piecewise function, I like to just go ahead and step through my continuity conditions and then just spell everything out, and it gives me a structure for me to see where things land for this problem. So what we can do first is look to see, does the point exist? Okay. Second condition, does a limit exist? That means as we approach C from the left side and from the right side, are they in agreement? Sometimes we need one side limit if there are piecewise functions defined on either side of C, but other times we're able to just rely on one limit statement. So we have a couple tools available to help us decide if the limit exists. And finally, for the condition 3 is we look at the results of the first two. If the first value produces a y value for our point, and if a limit exists, do those two results agree? If they are in agreement, that means the limit exists where the point exists, and we know that for sure the graph is going to be continuous through that point C. All right, so let's go through our conditions here. Our C value is 2. That's whenever we're concerned about where our c value is, we just look to see what point that this problem is kind of centered around. So we're talking about 2 here. So first condition, does the point exist? F of 2. F of 2 is equal to 7. So the first condition passes. Okay. Second condition, does the limit exist? Now, something we got to be careful of is we don't need one-side limit for this, because this is not less than and greater than. Okay? If it were, then we have 2 separate branches that we have to rely on one-side limit. Here, this is not a connected graph. This is just a point. So the connected graphs on either side of 2 is all contained within this, because this graph exists to the left of 2, exists to the right of 2. It just doesn't exist at 2. So this is the same thing as saying this graph is for the left side of 2, less than 2, and this is also for greater than 2. Now, if the function look more like this, like number 4, and we have to find limit, then we got to rely on one-side limit, because we have different graphs defined on either side of 2. But here, everything is self-contained within this first function. So we can just rely on finding the limit of that first expression. Okay, we can first thing we do is we plug in 2. We're going to get 8 minus 6 minus 2, which is 0. Plug in 2 into the denominator, we get 0 over 0. So we could go through L'Hopital's rule, or we can go through factoring. Here I just decided to go through the factoring method. So I factored the numerator. I saw that there was a common factor. I reduced it. So I reevaluated. So I removed the cause of that 0 over 0. Reevaluate it, plug 2 in for the remaining x. 2 times 2 is 4, 4 plus 1 is 5. So the limit as x approaches 2 of f of x is equal to 5. First condition passes, second condition passes, but now the third condition is looking to see, do these two results agree with each other? Are these equal? So f of 2 is 7, but limit is 5, so 7 doesn't equal to 5, so therefore we have a hole in the graph. The limit exists, but the approach from both sides is different from where that point is defined. So this is a removable discontinuity at x equals 2. Okay, number 4, look at the function for f of x. For what value of b is our function continuous at x equals 2? So again, I'm just going to go through my continuity conditions here. First condition, does the point exist? So at 2, the point is defined at this first piecewise function because of the equal sign here. So f of 2 is equal to e to the 2b. Looks like I don't know what b value is, so I'll just leave that alone. And then second, does the limit exist? So here we do have different graphs defined on either side of 2. So it's different graph to the left side of 2 versus the definition of our function to the right side of 2. So we need to rely on one-side limits. So we need to find the limit as x approaches 2 from the left side of 2. That's for e to the bx. So if we plug x, replace x with 2, we get e to the 2b. Remember, when you see one-side limit, you're just going to plug in that whole number. Don't do anything with decimals. Okay. All right, limit as x approaches 2 from the right side of 2. First thing we do, identify the piecewise function that is appropriate for the right side of 2. That's the 1.5x plus b. Plug 2 in for x, and we get 1.5 times 2 plus b, which is 3 plus b. So now, if we want the function to be continuous, we need these two results to be equal to each other. Okay. So we're going to set e to the 2b equal to 3 plus b. This is not something that we can solve by hand easily, so let's bring everything over to one side. And we have e to the 2b minus b minus 3. So now I'm just going to graph this function. And when I graph this function, if I graph a function of y is equal to e to the 2x minus x minus 3, I'm going to get this curve. And I'm just looking for where this graph is equal to 0. So I'm looking for the x-intercept, use the second trace 0 feature, and we can narrow down our, isolate our x-intercepts to be negative 2.998 and 0.647. All right, number 5. Limit as x approaches 6 of f of x. exists with limit as x approaches 6 of f of x is less than 5, and f of 6 is equal to 10, which of the following statements must be false? Okay. So if we want to look at this graph here, we know that our f of 6 equals 10, so I know my order pair is going to exist. I know my limit is going to exist, but it looks like it's going to be at approaching a y value that's less than 5. So I just created a situation where it's less than 5. Now, just an arbitrary graph just to kind of help me have a visual of this. And it says which of the statement must be false. The limit as x approaches 6 from the left side is equal to 0. Now the graph here I'm showing doesn't equal to 0 here, but it could be, right? There's no restriction that says that it can't be 0, so this could be true. Limit as x approaches 6 from the right side of 6 is less than 5, so this has to be true, right? We're told that the full limit is less than 5, so that means the one-side limit must also be lower than 5. Okay. Limit as x approaches 6 from the left side of 6, okay, so this branch, is equal to this branch. And we know that's true because we're told that the limit does exist, so the one-side limit it's a foregone conclusion that both sides must also be in agreement. Now, is the function continuous at x equals 6? Now, this one we know has to be false because we're told that the limit is less than 5, and the order pair is at 10, so there's no way that these two can be in the same location. So we know that there must be a hole, which means that there is a removable discontinuity at x equals 6, which means the function is not continuous. Number 6, I see a piecewise function. Let g be the function defined where k is a constant. For what value k is g continuous? So I see a piecewise function with continuity involved, so I'm just going to go through my continuity conditions. Okay. So the first thing, does the point exist? My x value is at negative 3. So negative 3 is for the second piece, for the second defined value here. So f of negative 3 equals k. That's as far as I can go. I don't know what k value is yet, so we'll leave that alone and move to the next condition. Does the limit exist? Again, we only have to rely on one statement because there's no need for one-sided limits because everything is self-contained within this expression. This is defined on the left side of negative 3. This is also defined on the right side of negative 3. So we just need one limit statement here. Plug in the negative 3, we get 9 minus 9, which is 0. Plug negative 3 in, we get negative 12 plus 12, which is 0. 0 over 0, we can go through L'Hopital's rule, but here I just decided to go through factoring. So I factor the numerator, I factor the denominator. X plus 3 are common factors that I can reduce. I can reevaluate my negative 3. So negative 3 minus 3 is negative 6 over 4 equals negative 3 halves. The limit is at negative 3 halves. And now the third condition, if we want the function to be continuous, that means first conditions, the result from first condition and the result from second condition, they must equal each other. So if we want this to be continuous, then k must be equal to negative 3 halves, and that is our answer.